Introduction to derivatives. Goals: want to understand the relationship between a secant line and the average rate of change. This is something that you should have done in like pre-calculus or algebra, but you may not have seen the secant line terminology. Understand the relationship between a tangent line and the instantaneous rate of change. And this is where we're going to have to use derivatives eventually to find this, but I want you to see it visually. And then know and be able to use the definition of a derivative. So we're going to look at using limits, which we've been building up to this point, in order to evaluate a derivative using that definition. So first thing here, secant lines and the average rate of change. So in algebra, you use the slope to find the average rate of change between 2 points. And that average rate of change formula then, using the slope format, would become f of x2 minus f of x1 up in the numerator, that's your y difference, and then divided by x2 minus x1. Another way that you might see this written is this delta y over delta x. And in math, that little delta symbol just stands for change in. So the change in y over the change in x. It's really what that's saying. So graphically, what does this look like? And if we were to just take a kind of basic curve here and pick a point x1 here, which would give us the f of x1 here, and then x2 maybe over here with the f of x2 matching up right here. For the average rate of change, you're really looking at the slope of the line that connects those 2 points. So the slope of that line is the average rate of change between x1 and x2. And furthermore, the line that we drew that connects those 2 points is called a secant line. So in a graph, when you're connecting 2 points, you can think of that as the secant line. So started out with the slope, looking at that secant line, gave us the average rate of change. Well, let's move into tangent lines now and look at the instantaneous rates of change. So while the average rate of change is useful, the instantaneous rate of change is also an important concept. Probably more important as you move forward in higher level math, physics, engineering. That's really what you're going to be focusing on. So how is it found? Well, let's consider the following here. And again, I'm just going to have this basic same curve. I'm going to put the x1 in basically the same location. So our f of x1 shows up here. And I'm going to start out with the x2 over here. This f of x2. So you're probably saying it looks exactly like the same picture from up above. But really what's going to happen here is we're going to let x2 get closer and closer to x1. So I'm just going to keep seeing, at this value, a new y, and I'm going to let this one come down, this one come down, and this one come down. I'm just going to keep letting the x1 driven point get closer and closer and closer, and this is where the limit comes in. It's basically going to get infinitely close to that x1. And all these different secant lines that you might have had, maybe started here with the secant line, and you got to this, and then this one, and then this one, and then this one. And then eventually what's going to happen when you let that second point get so close to the first point that you can hardly tell the difference between them, they're infinitely close to each other, what you're going to get here is a line that essentially touches the graph at 1 point. What could be thought of as 1 point. So again, you're letting that x2 get closer to x1 until they're essentially the same point or same location, more importantly. And that is, in a limit sense, you're going to let x2 approach x1. So one thing to note then is that the slope of this tangent line is now going to be the instantaneous rate of change. So the secant line, slope of that is your average rate of change. Tangent line, the slope of that is going to be the instantaneous rate of change. So this concept then of instantaneous rate of change is going to lead us to the derivative. And what we're going to see here, same basic curve just for the sake of exploring this. And instead of an x1 here, so if you already drew that, sorry, we're going to replace this with kind of in general this a. Stands for some x value. And then over here, we're going to start out with some a plus h. So that's replacing like the x2. And what we're going to do here then is we're going to have this a related to an f of a. And we're going to let the distance between a and a plus h get smaller and smaller. So similar to what we did on that last slide, but now using this new notation that we're going to see in the definition. And essentially, we're going to get h going to 0. We're going to let this h approach 0. So what's going to happen then is at this a plus h location, as h goes to 0, it's going to get closer, 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 closer. And the points on here, starting on the graph, we're going to see these things get closer, 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 closer. So as h is going to 0, what's happening here is that the distance between those 2 points we're using is getting smaller and smaller and smaller, and that will essentially allow us to find the slope of the tangent line when we put the 2 points into a slope formula and let h go to 0. So then the definition of the derivative using this new a and a plus h notation is going to be as follows. The derivative, of a function f at a number a denoted by f prime of a. So this is now going to be your derivative notation. That little symbol there is prime. Looks like an apostrophe in English. Really, if you're typing it, it's an apostrophe in English. But in math class, calculus, we now are going to say this is f prime of a. And the definition is f prime of a equals the limit. Here's where all that limit stuff we did is going to come into play. As h goes to 0 of f of a plus h minus f of a all over h. And one thing to note about this definition, if you did a plus h minus a, the two different x values subtracted, you would just get h there. The a's would add to 0, go away. So when you see that h down below, don't lose sight of the fact that it's still a difference in x's, and up top, we still have a difference in y values. We got f at a plus h, and we got f of a. So we are still using the slope formula as the basis of our function derivative to make this happen. And then we just let that limit occur so that these points get closer and closer together, and we essentially end up with that tangent line. And more importantly, f prime of a is going to be the slope of that tangent line. So you do all this if the limit exists. If the limit doesn't exist, well, then you have issues. So note that the result is a slope. I know I've said this a couple of times, but this is one of the most important things that I want you to take away from this derivative concept. Derivative is a slope. The derivative is a rate of change. It's just at an instant instead of an average. So we can use the definition of the derivative to find the derivative of the following function at x equals 2. So we're going to start out here with f of x equals x squared plus 5. And what we're looking for then is f prime of 2, the derivative. And we get this limit as h goes to 0. F of 2 plus h, the target value that we're looking at, is 2 as what was given. And so we'll have this f of 2 plus h minus f of 2 all over h. And this will then equal the limit as h goes to 0 of 2 plus h, quantity squared, just plugging that in for the x in the function, and then plus 5. And then minus, we're going to plug 2 into the function, and we got to subtract the whole result away. So that's why I'm putting parentheses here. So we get that 2 squared plus 5, and then this is over h. And then this will equal the limit as h goes to 0. Got to FOIL out that 2 plus h quantity squared, so we'll get 4 plus 4h plus h squared, and then still plus the 5. And if you evaluate what's in the parentheses here with the 2 squared plus 5, you get 4 plus 5, or 9. So I'm going to just subtract off 9 off the end there. And then that's still all over h. And now where's the things that we can simplify? Well, 4 plus 5 is 9. 9 minus 9 goes away. So we have this limit still. We haven't done the limit yet. And we have a 4h plus h squared left in the numerator over h. And now I want to simplify even further. Up top, there's a common h to both those terms. I could factor it out, cancel it with the h down below. So using some algebra skills here. And what you're left with is just 4 plus h. And now you let h go to 0, and you get 4. So the derivative value is just 4. And what that tells me then, if I were to graph x squared plus 5, and you can do this on your own, and then look at different tangent lines, and we're going to get this here shortly, at x equals 2, the slope of the tangent line would be 4. Okay, so we can also then use the derivative result to find the equation of the tangent line at A. So how? Well, we're going to use the point slope form of a line with the slope replaced by our derivative. So you have that y minus f of a, our target value, equals f prime of a, whatever our target x was. Up above it was 2, and then you have x minus a. So if we just let the a be 2, using what we had from up above, and we're going to let the f of x again be this x squared plus 5 that we used in the above example, what we're going to get here then is y minus f of 2 equals f prime of 2, which we already found right here, it's 4, and then times x minus 2 in parentheses. And f of 2, if you plug 2 into x squared plus 5, you get 9. F prime of 2, the slope of the tangent line, is going to be 4 from the work we did in that f prime of 2 using the limit up above. You have x minus 2. And then if you do a little manipulation here, you would get that y equals 4x plus 1. And this is the tangent line to the curve at x equals 2. And just want to show you the graph of this. If you go over to Desmos, put in the x squared plus 5, the red parabola, graph that tangent line that we created using our derivative for the slope, our f prime of 2 for the slope, you can see that at x equals 2, which is right there, 2 and 9, you have a tangent line in the blue. And the slope of that tangent line, if you kind of look from one point to the next, is 4. So over 1 up 4, which is your derivative. All right. Thanks for watching.